The paper we will discuss today is the IFMIF-DONES project Preliminary Engineering Design. Chapter 1.5 Test Systems. The test systems from the core of the plant and include the systems required to accommodate a HFTM under controlled environment and conditions for irradiation, as well as the system required for handling the HFTM and transporting the irradiated HFTM for further external processing, and post-irradiation experiments. A set of ancillary systems provides the electrical distribution, cooling, vacuum, and supplying and purification of gases. The test code depicted in Figure 5 is the closed cavity or chamber for housing the lithium target assembly, lithium quench tank, and HFTM. At the top, two shielding plugs are designed to close the TC during the irradiation period for protecting the access cell AC, which is located directly above the TC from radiation. A test cell cover plate TCCP and a rubber-based sealing basket are applied to tighten the TC so that a controlled atmosphere inside the TC can be achieved. Gas pressure in the TC is different in the different plant status, but during operation it will be around 200 MBAR. Main criteria is that slight under pressure is required in relation with the one in the target assembly. The internal surface of the TC concrete shielding walls is covered by a closed stainless steel liner to maintain the gas tightness and to protect the concrete from contacting with lithium in case of a lithium spill inside the TC. Removable piping and coupling plugs PCPs are designed to accommodate all of the cables and PP pen penetrations, as well as to shield from gammas and neutrons. The major biological shielding includes the surrounding shielding walls, shielding stop plugs PCPs, and the TC floor between the TC and the lithium loop room below the TC floor. A test cell lithium system interface cell TLIC is arranged to accommodate thermal compensation sections of the inlet and outlet lithium PP. The basic configuration of the HFTM is illustrated in Figure 6, including one of its irradiation capsule assemblies, which enclose hermetically the material specimen stacks to be irradiated in the test module. The capsules thereby are installed in the container in so-called compartment slot. To achieve the temperature control of the specimen stack in the irradiation capsules, each capsule is equipped with at least 3 heaters, and each heater is monitored by 2 thermocapsules located inside the capsule in an inner vertical tube close to the center. The electrical power supply for each heater of a capsule is selectable independently to the others. Furthermore, capsules are filled with Na, besides the samples under irradiation, in order to promote the heat transfer, and each capsule is also surrounded in each slot by an insulation gap whose dimensions depend on the temperature of the corresponding compartment: 550 degree, 450 degree, 350 degree, and 250 degree. In addition to the heaters and the insulation gap, each slot is surrounded by mini cooling channels. The forcing coolant is helium at a pressure of 3.5 bar in the inlet. Very different specimen set can be arranged in this configuration depending on the specific irradiation needs at each camping. Typical proposals presently considered can be found in: a total of 24 capsules are installed in an 8x3 container having a 274 mm thickness in beam direction. 3 capsules in a row, or 32 capsules in a container 8x4 to 102.2 mm thickness in beam direction for capsules in a row, and are grouped in a capsule set. The container is supplied, as described previously, by helium to remove heat, nuclear and electrical from the capsules. The container itself is mechanically fixed to the attractment adapter assembly, which is positioned inside the TC by the support trusses assembly. A dedicated startup monitoring module (STUMM) is foreseen to be used during the commissioning phase of DONES to characterize the neutron, gamma, flux and spectrum, and to validate neutronic calculation models. The STUMM will be equipped with a wide set of instrumentation and positioned similarly to the HFTM as close as possible to DONES neutron source, i.e., just behind the helium target, lithium target backplate. Once the commissioning is completed, the STUMM will be replaced by the HFTM. The mechanical design of the STUMM will be very close to that of the HFTM. It will be fully compatible with the design of the TC and the forcing connections for other modules inside the TC. The characteristics of the sensor to be used in the STUMM are dependent on the resume of work of the module, however long radiation resistance and relatively low radiation sensitivity are required. On the other hand, since the module will be used in the commissioning phase, where different operation regimes are foreseen, the adapted sensor must be characterized by a wide dynamic range of sensitivity so as to allow detection and characterization of even small neutron fluxes. Most of the brand sensors are commercially available, but some of them will require ad hoc modification for IFMIF-DONES application, such as microfission chambers. New solutions are also being considered. Additionally, a collimated neutron beam facility, which takes advantage of the neutron flux behind the HFTM, has been incorporated into the IFMIF-DONES layout at this stage of the design. A dedicated experimental area has been planned behind the TC on the first floor of the IFMIF-DONES main building to accommodate a program of complementary experiments. Thanks for listening to the end of today's show.